Hello students, welcome to Microtheory. Let's start the course off by doing an overview of economic modeling. Economics is not a hard science like physics or biology, and so you shouldn't think of economic models as attempting to build a fully accurate picture of how the economy works. Because there's so many variables and interactions involved and different cases to consider that the complexity would become unworkable rather quickly. So instead, it's best to think of economic models as approximations that try to answer specific questions and focus only on the relevant details and make simplifying assumptions for everything else. For example, let's say I wanted to study a model of how shoppers in a grocery store chose what to buy. So I would just assume that every item on the shelves was just going to have some price. I wouldn't spend time conducting a detailed analysis of the specific conditions and variables that impact the production of every possible vegetable. And because economic models are necessarily approximations, they're never going to be completely accurate. There's always going to be different scenarios that don't obey the assumptions we've made, and so therefore don't match our conclusions. However, this doesn't mean that these models can't be useful, because ultimately the value of a model lies in how well it's able to predict future events. So for example, we typically take it for granted that firms always try to maximize profit. Now, strictly speaking, this isn't necessarily true all the time. We can think of plenty of instances where the personal taste of the management or maybe the reputational concerns are going to lead the firm to make choices that don't always yield the highest payoffs. However, assuming profit maximizing behavior is good enough, and that if we were to assume that firms always behave this way, our conclusions would match the actual outcomes closely enough to make our model useful. And ultimately, the test of any model's validity is how applicable it is to what we observe in the real world. Now, let's think about some features of economic models. The first is what we call the ceteris paribus assumption, which is Latin for all else being equal. Like we mentioned before, economic models cannot be all-encompassing. They have to focus on a particular problem that we wish to study. So for everything that we don't consider relevant, we just hold it fixed. So to continue our previous example, suppose that we wish to study how shopping habits might differ based on the day of the week. Then, we wouldn't allow for the possibility of some disease that wiped out half the tomato crop between Monday and Friday. Because while that certainly could happen, for the purposes of our model, it would only introduce additional complications that would make it more difficult to interpret results. Economists are going to divide the variables in a model between exogenous and endogenous variables. Exogenous variables come from outside of the model. They're going to be determined by factors that we aren't studying and aren't interested in trying to explain. They are simply given to us and treated as fixed. On the other hand, endogenous variables are determined within the model. And what we're typically interested in is how changes to the exogenous variables will affect the equilibrium values of the endogenous variables. So going back to our grocery example, from the perspective of a consumer, the prices are simply given. They may change from time to time, but it's in ways that they can't influence or control. On the other hand, the quantities of each item that they buy are endogenous, since they depend on the result of the consumer's internal optimization scheme. On the topic of optimization, you may have heard the common refrain that economists always assume that everybody is some type of perfectly logical homo economicus who always makes rational choices, and even though people in the real world often don't. In economics, rationality just means that you have some type of goal that you are consistently pursuing. It doesn't mean that this goal is necessarily a smart or a sensible one. So for example, if you have a social media star and their only objective in life is to maximize the number of likes they get on their videos, well, that person would still be behaving rationally, right? So long as they stick to this goal and never alter their priorities, even though that wouldn't necessarily fit our colloquial definition of what a rational person would do, right? The assumption is important because we don't always expect people to even clear this bar most of the time, but it allows us to set up an optimization problem with an objective function that the decision maker is maximizing or minimizing. And we can solve this problem to determine the resulting action they will take. Like we talked about before, while this isn't a perfectly accurate model of how people behave, it fits well enough to allow us to make predictions, and that ultimately is what we really care about. Finally, it's also worth pointing out the distinction between positive and normative economics. Positive or descriptive theories seek only to explain what's going on. They don't make any value judgments about what they observe. On the other hand, normative or prescriptive theories do take a position and often offer policy decisions as to what can be done to correct any problems. For example, on the topic of something like inflation, a positive economic model would only seek to find out the causes of inflation and then project the future trajectory given the available data. While a normative model might offer suggestions as to what can be done to bring the inflation rate to a subjectively reasonable level. In this diagram, we can see the structure of a typical economic model. It's taking in exogenous variables as inputs and then outputs values for the endogenous variables. For example, we typically assume that consumers and firms are price takers, in that they treat the prices as fixed and then choose the quantities of the goods that they would demand or supply. We can then use this model to study how the quantities would change in response to a change in prices. We don't use the model to explain how the prices would change. Let's look at an example where we have a price-taking firm that has a cost function C and chooses the quantity of output to maximize profit. So the profit, pi, is given by the difference between revenue, which is just price times quantity, and the cost, which is a function of the quantity, but isn't otherwise specified. So to maximize profit, we take the first derivative, the d pi dq, which is p minus c prime big P. Set that equal to 0. That gives us the first order condition, which is that price equals the first derivative of the cost function, which we call the marginal cost. So in other words, the additional cost incurred by producing another unit must exactly equal the price that this unit could be sold for. However, the first order condition is not enough by itself. We need to make sure that we're maximizing profit rather than minimizing it, and to do this we need to check the second derivative, d squared by dq squared, which equals minus c double prime of q. The second order condition here requires that the second derivative of the profit function be negative, so that minus c double prime of q is less than 0, or c double prime of q is greater than 0. Thus, in order to have a maximum, the marginal cost must be increasing, so that each unit costs more to produce than the last, so that you're going to keep producing as long as the marginal cost is less than the price and stop at the point where it's exactly equal, since any further units would be produced at a loss. So if we were to take the derivative of this first order condition with respect to price, so we have dp minus c prime of q star dp, and that's going to equal 1 minus c double prime of q star times dq star dp. We want to set that equal to 0. That we can solve to get dq star dp is equal to 1 over c double prime of q star. And since c double prime is positive, this thing is positive. So what did all this mean? This means that the optimal quantity is going to be increasing in the price, which gives us the familiar condition that our supply curve is going to slope upwards. The higher the price, the more we're going to supply. In economics, the market price of a good is generally taken to be the best assessment of how much it's actually worth. Though given how rapidly the prices of even the most basic commodities can fluctuate, people aren't always willing to accept that the market price is a fair or reasonable valuation, and so can often cling to this notion that a good has an intrinsic or true value that can differ substantially from the market value. So much of economic inquiry actually exists as an attempt to explain why there might be a disparity of how much something costs and how much it's quote-unquote actually worth, whatever that means. So this is demonstrated rather well in the famous water-diamond paradox, which asks why water, which is necessary for human survival, is available quite readily and cheaply, whereas diamonds, which really have no function aside from looking pretty, are so expensive and so sought after. One potential explanation for this is the labor theory of value, where the value of any good is determined by the cost of the labor necessary to produce it. Since water is everywhere, well, mostly everywhere, while diamonds are rare and costly to extract, the difference in price reflects a difference in labor costs. Now, while this might seem an attractive theory on the surface, it fails to take into account that not all labor is necessarily productive. So that while, yes, it requires a lot of time and effort to simply dig ditches and fill them back up again, there isn't any reason to do this. And so all of the labor that goes into doing something like that is not actually creating any value. A better explanation for the water-diamond paradox is that, while water is important, most of us are pretty well hydrated as it is. So drinking an additional glass of water isn't going to do a lot for the average person. On the other hand, most people don't own that many diamonds, if at all. So the marginal benefit of owning a diamond is quite high. And in a situation, such as if you're at a concert or a baseball game, where there's a lot of thirsty people and concession sales are tightly controlled, water, unsurprisingly, is far more expensive than usual. So when we're conducting economic analysis, we need to focus not on the aggregate value that consuming a good might have, but rather the value that an additional unit would bring, or how much that next unit would cost to produce. So everything interesting in economics happens on the margins. So here we have a picture that you should all be familiar with already. In economics, we plot quantity on the x-axis, price on the y-axis. So we have the intersection of an upward sloping supply curve and a downward sloping demand curve. The intersection gives us the equilibrium. So we have a price of P star and a quantity of Q star. The equilibrium price is going to represent both the marginal cost of production as well as the marginal benefit to the marginal consumer. Let's look at a simple example where we have linear supply and demand curves. So we have QD here and QS here, and to find the equilibrium, we have to set QD equal to QS. So if you take these two equations and we rearrange, we have 225p is equal to 1125. That gives us an equilibrium price of 5. Now, if we were to take this price of 5, we can plug it into either of these equations. That'll give us the equilibrium quantity, which is going to be 500. In general, if we have a demand curve that's linear and a supply curve that's also linear, that's going to give us an equilibrium price of A minus D over D minus B. So demand curves are typically downward sloping, so B is going to be negative, and the whole denominator will be positive. Here, we can think of these parameters, A, B, C, and D, as exogenous variables. So these variables are going to be some factors that influence supply and demand. On the other hand, the equilibrium price and quantity are going to be our endogenous variables. These are determined from within the model. If we change one of the exogenous variables, that's going to cause either the supply curve or the demand curve to shift, which is going to move us to a new equilibrium. Let's imagine that we increase A. So increasing A means that there's going to be an increase in demand. We can see that the effect of increasing A on the equilibrium price is going to be equal to 1 over D minus B, which is positive. That tells us that increasing demand will increase the equilibrium price. Now let's imagine the effect of increasing C, which reflects an increase in supply. That's going to be equal to minus 1 over D minus B, which is going to be negative. So an increase in supply will decrease the equilibrium price. So for example, let's say A increased from 1,000 to 1,450. This is going to move the demand curve up and to the right, and so the equilibrium will move in the same direction. So graphically, it's going to look something like this. Old demand curve, here's a new one. You can see here's our old equilibrium, here's our new one. Both the equilibrium price and quantity should increase. So let's show this mathematically. If we solve here, what we're going to get is that 225p equal 1575. That gives us a new equilibrium price of 7. Before it was 5. Now if we plug in 7 into either the supply or the demand function, we're going to get an equilibrium quantity of 750 compared to 500 before. So we can see that both the equilibrium price and quantity increased as a result of an increase in demand. Whenever we shift either the supply or the demand curve, the equilibrium moves along the other curve. So shifting the demand curve means the equilibrium moves up the supply curve. Supply curves are upward sloping, so price and quantity move in the same direction. Let's think about the economic intuition. If the demand for a good increases, then there are both more people who are willing to buy it and they're willing to pay a higher price for it. This basic model is an example of a partial equilibrium, where we study only a single market in isolation, and by the ceteris paribus principle, assume that all other markets remain unaffected. However, in real life, markets are all interconnected and interrelated. So if we are moving to a new equilibrium in this market, this is going to cause shifts in other markets, which causes them to move to new equilibrium. Then this could cause feedback, which would cause further shifts in this market, and so on. So to properly analyze an economy, we need to study a general equilibrium, where all markets reach equilibrium simultaneously. This is a rather complex and computationally intensive task, so we can start by studying the types of relationships between different markets. On a basic level, the production of different goods utilize the same resources. So allocating resources means that there's an inherent trade-off. The more labor that we use to produce food, the less labor we have available to produce clothing, and vice versa, and likewise for any other good. Regardless of what monetary cost there might be to employing these resources, there's always an opportunity cost, and that allocating more resources toward one good means that we must allocate less to another. So we can measure the cost of producing more of one good in terms of how much of the other good we have to sacrifice to free up the necessary resources. not all allocations of resources are equally valid either. If we were to say to plant crops in the city and build clothing factories in the countryside, we'd probably end up with a lot less of everything than if we were to allocate our land more wisely. What does this tell us? It tells us that some allocations are efficient in the sense that we're making the best use of available resources, while other allocations are wasteful. They're going to leave some output on the table. So one of the central pillars of classical economic theory is that markets will naturally find an efficient allocation on their own, as if they're guided by a quote-unquote invisible hand. We're going to reach an efficient allocation on our own without requiring any kind of outside interference by an entity such as the government. If we look at this diagram, it's called production possibilities frontier. The y-intercept is going to tell us the total amount of food we could produce if we allocated everything toward producing food. As we shift resources away from food and towards clothing, we're going to move down the frontier until we eventually reach the x-intercept. The x-intercept is going to be the point where we allocate all of our resources toward producing clothing. So importantly, the production possibilities frontier is always going to be curved outward. What this tells us is that we can generally produce more overall if we balance our resources between the production of food and the production of clothing, rather than just focusing on one or the other. We get a little bit more by dividing our resources between these two goods. So why is this? If I want to look at the opportunity cost of clothing, that's going to be measured in terms of how much food I have to give up to produce more clothing. And as you can see from this graph, the opportunity cost of clothing is going to increase as I move down the production possibility frontier. Up here, where we're producing mostly food and very little clothing, we can gain a lot of clothing by sacrificing only a little bit of food. Down here, after we've already shifted a lot of our resources away from food and towards clothing, we have to give up a lot of food to gain just a little bit of clothing. So let's look at this mathematically. Let's say that X is the total amount of clothing and Y is food. And both of them are going to be produced using a single resource, which is a labor, L, that's going to be shared between the output of these two goods. We're going to have a total labor force of 200. So it means that Lx plus Ly is less than or equal to 200. We can use up to 200 units of labor between X and Y, but we can use less if we want to. The output of X and Y is going to be determined by these production functions. To construct the production possibilities frontier, we're going to plug in for Lx and Ly. So Lx is going to be equal to x squared, and Ly is going to be equal to y over 2 squared, so y squared over 4. The production possibilities frontier is that it's going to be given by this equation, x squared plus y squared over 4 is less than or equal to 200. So if we are to rearrange this equation, we're going to get that y is equal to the square root of 800 minus 4x squared. So this is going to be the equation for an ellipse, at least the upper right quadrant of an ellipse. To find the opportunity cost, we want to take the derivative of this function to get the slope of the production possibilities frontier. So to find the slope of the production possibilities frontier, we want dy dx, and we can get this using the chain rule. So we're going to have 1/2 times this argument to the minus 1/2 times the derivative of the inside, which is minus 8x. We can also write this as minus 4x, and this is just y. What we can see from this expression is that as we move down the production possibilities frontier, so as x increases and y decreases, the slope is going to become steeper. What this means is that to produce each additional unit of clothing requires giving up more and more food. Another thing to pay attention to is that this production possibilities frontier comes from the constraint that we have a total labor force of 200. And this equation assumes that we're going to be using all of the available labor. However, we don't necessarily have to. For example, let's imagine that 20 workers are going to be permanently unemployed and we're only going to be using 180 units of labor. What's that going to look like? Well, we have our production possibilities frontier here. This would give us a point inside the production possibilities frontier. So we can produce anything out here and anything inside. However, the points inside are clearly not production bundles that we would want to choose because we can get more of everything if we just utilize all the resources that we have. So the production possibilities frontier tells us what we can produce. We can always produce less than this, but we would never want to. So far, we've established a rudimentary conception of economic models. We've made some assumptions about how firms and individuals are going to behave, and we applied some basic techniques to draw some conclusions about what kind of market phenomena we would see as a result. However, economics, like most fields, is constantly advancing. We're always developing new tools and techniques to broaden our understanding. So for example, the field of behavioral economics challenges the standard assumption that individuals behave rationally and investigates the types of psychological biases that could lead people to behave in supposedly illogical ways. Furthermore, while our standard models are going to assume that all parameters are common knowledge to all market participants, newer models that allow for uncertainty and asymmetric information introduce components of risk and strategic behavior. We didn't look at those here. And finally, the availability of ever greater computing power means that economists are able to analyze far larger and more comprehensive data sets than ever before. This means that we're now able to directly answer questions using empirical methods that were only ever abstract thought experiments before. The aim of this course is to arm you with enough knowledge of all of the important concepts in microeconomics to make sense of all these exciting new developments, and potentially for you to contribute to them in the future.